The expectation seemed reasonable at first. A galaxy containing hundreds of billions of stars, many of them older than the Sun, should have had enough time to produce not just life, but civilizations far more advanced than ours. When radio telescopes first turned toward the sky in the middle of the 20th century, the assumption was not whether signals would be found, but when. The logic was straightforward. If even a small fraction of stars hosted planets, and even a small fraction of those planets developed life, and even a small fraction of that life became intelligent, then the Milky Way should already be filled with technological societies. Some of them would be millions of years ahead. Their presence should be visible, measurable, impossible to ignore. But as the decades passed, the silence remained absolute. So not a single confirmed transmission, not a single artifact, not even a clear anomaly that could not be explained by natural processes. The instruments improved. The search expanded. Entire programs were dedicated to scanning the sky across different frequencies and directions. Yet the result did not change. The universe offered no reply. This contradiction became known as the Fermi Paradox. The question it poses is simple, but it carries weight that grows with every new observation. If the conditions for life appear common, and if time has allowed for its development, then where is everyone at first? The answers were optimistic. Perhaps civilizations are rare, but not impossibly so. Perhaps they are too far away, their signals too weak to reach us. Perhaps we are simply early among the first to emerge. These explanations allowed the silence to feel temporary, a gap in knowledge that would eventually close. But as more data accumulated, the optimism began to weaken. New discoveries did not make the paradox smaller, they made it sharper. Each confirmed exoplanet, each refined estimate of habitability, each deeper survey of the galaxy added pressure to the same unresolved question. The universe was not just quiet, it was consistently, persistently quiet across every method we had devised to listen. And that is where the problem begins to shift, because at some point, silence stops being a lack of evidence and starts becoming a form of evidence itself. The expectation did not emerge from speculation alone. It was built on measurable quantities. By the time astronomers began identifying planets around other stars in the 1990s, the older estimates that treated planetary systems as rare began to collapse. Data from missions such as Kepler's Space Telescope revealed that planets are not exceptions, but the default outcome of star formation. Within a few years, thousands of exoplanets had been confirmed, and statistical analysis suggested that most stars in the galaxy host at least one planet. The question shifted from whether planets exist to what kinds of planets are common. Among those discoveries were Earth-sized worlds orbiting within regions where liquid water could exist. These regions, often called habitable zones, were once considered narrow and rare. Yet observations showed that such zones are widespread. Systems with multiple planets became routine. Some stars hosted tightly packed configurations, others displayed gas giants migrating inward, and many showed stable orbits that could persist for billions of years. The raw ingredients for life, energy from a star, stable orbits, and chemical complexity, appeared again and again. This led to a more structured attempt to estimate how many civilizations might exist. In 1961, Frank Drake proposed a framework now known as the Drake equation. It did not provide a single answer, but broke the problem into factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction that develop life, the fraction that develop intelligence. the fraction that produced detectable technology, and the length of time such civilizations remain detectable. Early estimates filled these variables with optimistic values, often yielding thousands or even millions of civilizations in the Milky Way alone. At the time, those assumptions seemed reasonable. Earth offered a single data point, but it demonstrated that life could arise from non-living chemistry, that intelligence could evolve, and that technology could spread signals beyond the planet. Given enough time and enough planets, repetition appeared inevitable. Evolution, while unpredictable in detail, showed consistent patterns, increasing complexity, adaptation to environments, and occasional leaps in capability. Intelligence, once achieved, provided a survival advantage through tool use and cooperation. From that perspective, technological civilizations were not anomalies, but expected outcomes. The duration of those civilizations became a critical variable. If a society could survive for hundreds of thousands or millions of years, even a small number of such societies would overlap in time and space. Communication would not require synchronization. Signals would travel across vast distances, accumulating as a background of detectable activity. Even if direct contact were rare, indirect evidence, radio leakage, engineered structures, or alterations to stellar environments should be observable. This reasoning extended beyond communication. Advanced civilizations, given sufficient time, might expand beyond their home systems. The energy requirements for interstellar travel are high, but not physically impossible. Probes traveling at a fraction of light speed could cross the galaxy in timescales far shorter than its age. Self-replicating probes, in particular, could spread exponentially, exploring or even modifying large regions of space. If even one civilization had pursued such a strategy millions of years ago, traces of its presence should be widespread. Yet when astronomers examined the sky with increasing precision, they found no evidence of such activity. Stars appeared natural. Galaxies followed expected distributions. Infrared surveys searching for waste heat from large-scale engineering projects, sometimes referred to as Dyson structures, revealed no clear candidates. Radio searches detected natural emissions from pulsars, quasars, and interstellar gas, but no confirmed artificial signals. Each new instrument expanded the search, and each expansion returned the same result. At this stage, the paradox was still manageable. The variables in the Drake equation were uncertain, and adjustments could reconcile the silence with theory. Perhaps the fraction of planets that develop life is far smaller than assumed. Perhaps intelligence is a rare evolutionary outcome rather than a common one. Perhaps technological civilizations tend to destroy themselves quickly, reducing the window during which they are detectable. Each of these possibilities acted as a filter, reducing the expected number of observable societies. But there was a deeper issue embedded in the equation. Many of its variables are not independent. The emergence of life depends on planetary conditions, which depend on stellar type, which depends on galactic environment. The evolution of intelligence depends on stable climates, long-term energy availability, and the absence of catastrophic disruptions. When these dependencies are considered together, the optimistic estimates begin to narrow. What once appeared as a wide range of possibilities starts to compress into a smaller set of viable pathways. Even so, the data continued to push in a direction that should have increased expectations, not reduced them. The discovery of extremophiles on Earth showed that life can exist in environments once considered hostile: deep ocean vents, acidic lakes, and frozen deserts. This expanded the range of conditions under which life might arise. Organic molecules were detected in interstellar space, indicating that the building blocks of life form naturally. Meteorites were found to contain amino acids, suggesting that prebiotic chemistry is not confined to planetary surfaces. All of this reinforced a simple idea. The ingredients are common, the environments are varied, the timescales are immense. Under these conditions, repetition should occur, not once, but many times. And yet, despite every refinement in observation and every expansion of theoretical models, the central question remained unchanged. If the processes that led to life and intelligence on Earth are not unique, then why has no other example made itself known? The paradox was no longer just a question of missing signals. It was a conflict between two lines of evidence that should agree, but do not. On one side, the galaxy appears fertile, filled with planets and chemical potential. On the other, it appears empty of any detectable technological activity. Reconciling these two observations requires more than adjusting a single variable. It requires identifying a mechanism that consistently prevents the expected outcome. And that is where the first real cracks begin to appear. Those cracks did not appear suddenly. They emerged as measurements became more precise and assumptions were tested against data rather than optimism. One of the first revisions concerned the idea of habitability itself. Early models treated the habitable zone as a simple orbital distance where liquid water could exist on a planet's surface. But as planetary science advanced, it became clear that distance alone is not enough. A planet can sit in the correct region and still be uninhabitable due to atmospheric composition, magnetic field strength, geological activity, or stellar behavior. Observations of exoplanets revealed environments far more volatile than expected. Many stars, especially smaller red dwarfs, exhibit intense stellar flares capable of stripping atmospheres over time. Planets orbiting close enough to remain in the habitable zone around such stars are often tidally locked, exposing one side to constant radiation while the other remains in permanent darkness. Without a stable atmosphere or magnetic field, surface conditions can degrade quickly. What once appeared to be a wide band of potential habitats began to narrow when these factors were included. Earth itself provided a reference point that, instead of simplifying the problem, complicated it. The planet's long-term stability depends on a combination of factors that are not guaranteed elsewhere. Plate tectonics regulates carbon dioxide through a feedback loop involving volcanic activity and weathering, maintaining temperatures within a range that allows liquid water to persist. The presence of a large moon stabilizes axial tilt, reducing extreme climate variations over geological timescales. A magnetic field protects the atmosphere from solar wind. These systems interact in ways that create a stable environment, but each one depends on conditions that may not be common. Further constraints emerged from the timing of events in Earth's history. Life appeared relatively early, within a few 100 million years after the planet cooled. However, complex multicellular life took billions of years to develop. During that time, Earth experienced mass extinctions triggered by asteroid impacts, volcanic activity, and shifts in atmospheric composition. Each extinction reset evolutionary progress, and only a small fraction of lineages survived. Intelligence, as it appears in humans, is not simply the result of time passing. It is the outcome of a specific sequence of events, many of which could have unfolded differently. Astrophysical threats added another layer of uncertainty. Gamma-ray bursts, though rare, release immense energy capable of affecting planetary atmospheres across large distances. Supernovae can expose nearby systems to radiation levels that disrupt biological processes. The distribution of such events is not uniform across the galaxy. Regions closer to the galactic center experience higher densities of stars and consequently higher rates of energetic events. This creates zones where the development of complex life may be repeatedly interrupted. When these factors are combined, the number of planets that remain continuously habitable over billions of years becomes smaller than initial estimates suggested. Not zero, but reduced. The concept of a galactic habitable zone emerged, by describing regions where conditions are more favorable for long-term stability. Even within these regions, individual planetary systems must meet additional criteria to support the gradual evolution from simple organisms to complex ecosystems. This shift did not eliminate the possibility of life elsewhere, but it reframed the probabilities. Instead of assuming that life emerges wherever conditions allow, the focus moved toward identifying the precise combination of factors required. Each added requirement acts as a filter, reducing the number of planets that pass through to the next stage. A planet must form in a stable region, maintain an atmosphere, avoid catastrophic sterilization events, and sustain environmental conditions long enough for evolution to proceed. The concept of filters began to take shape not as a single barrier, but as a sequence. Some filters operate early, preventing life from emerging at all. Others act later, limiting the development of complexity or intelligence. Still others may occur after intelligence arises, affecting the longevity of technological civilizations. The cumulative effect of these filters determines how many civilizations exist at any given time. At this stage, the reasoning still allowed for optimism. Even if each filter reduces the number of candidates, the initial number of planets is so large that some should still pass through. The galaxy contains hundreds of billions of stars. Even a tiny fraction of habitable worlds could yield multiple civilizations. The silence, therefore, required either that the filters are far stronger than expected, or that an additional mechanism is at work. And this is where the problem deepens. Because if the early filters are not sufficient to explain the absence of evidence, then attention must turn to the later stages, after life has already begun to develop. If life can emerge and persist long enough to produce complexity, then the next step is not guaranteed to follow. Intelligence is not a simple extension of evolution. It is one pathway among many. On Earth, for most of its history, life existed without anything resembling human cognition. For billions of years, ecosystems were dominated by organisms that adapted successfully without developing advanced problem-solving or technology. Evolution does not aim toward intelligence. It favors traits that improve survival in specific environments, and in many cases, those traits do not require abstract reasoning or tool use. Even within the relatively recent history of complex life, intelligence comparable to humans appears only once. Other species demonstrate varying degrees of problem-solving ability: cetaceans, corvids, primates, but none have crossed the threshold into sustained technological development. This suggests that the emergence of intelligence capable of building civilizations may depend on a narrow set of conditions. It requires not only cognitive capacity, but also environmental pressures that reward its use, physical structures that allow manipulation of tools, and social systems that support the transmission of knowledge across generations. The development of technology introduces a new dynamic. Once a species begins to alter its environment intentionally, it gains the ability to accelerate change. This can lead to rapid advances, but it also introduces risks that do not exist in purely natural systems. Energy use increases. Resource consumption intensifies. New forms of instability emerge, both ecological and social. A civilization capable of transmitting signals across space must first pass through a phase where it learns to manage these risks. Historical examples on Earth illustrate how fragile complex systems can be. Societies have risen and fallen due to resource depletion, environmental changes, and internal conflict. While none of these events have erased humanity as a whole, they demonstrate how quickly organized systems can collapse. On a planetary scale, the stakes are higher. Technologies that provide significant advantages, such as advanced energy systems or synthetic biology, also carry the potential for large-scale disruption if misused or mismanaged. This leads to the idea that there may be a stage in the development of intelligent life where the probability of failure increases sharply. A species reaches a level of technological capability that allows it to influence its own survival on a global scale, but not yet the stability or foresight to manage that influence effectively. During this period, the risk of self-inflicted collapse may be higher than at any previous stage. If this pattern is common, it would act as a filter that operates after intelligence emerges. Many civilizations might reach this threshold, but few would pass through it. The duration of technological detectability would then be limited, reducing the likelihood that two civilizations overlap in time. Signals would be brief, scattered, and difficult to detect across interstellar distances. However, this explanation introduces its own tension. Even if most civilizations fail, it only takes a small number to succeed for the galaxy to become visibly active over long timescales. A civilization that stabilizes its development and continues for millions of years would have ample opportunity to expand, explore, or at least leave detectable traces. The absence of such traces suggests either that success is extremely rare or that successful civilizations behave in ways that do not produce easily observable signals. Another possibility is that technological progression itself leads to changes that reduce detectability. Early human technology produced strong, unintentional radio emissions that leaked into space. Over time, communication methods have become more efficient and less broadcast-oriented, reducing the amount of energy radiated outward. A more advanced civilization might rely on communication systems that are highly directional, encrypted, or based on physical principles we do not yet understand. In that case, the absence of signals would not indicate absence of activity, but a mismatch between our detection methods and their technologies. This shifts the focus from the existence of civilizations to the visibility of their actions. The question is no longer only how many civilizations exist, but how many produce signatures that can be detected across interstellar distances using current methods. If detectability decreases as technology advances, then the most visible phase of a civilization may be its earliest and therefore its shortest. Yet even this does not fully resolve the contradiction, because the universe does not only offer one channel for detection. Beyond radio signals, there are potential indicators such as large-scale energy use, atmospheric modifications, or artificial structures. The absence of these indicators across extensive surveys suggests that either such activities are rare or that they are conducted in ways that minimize external signatures. At this point, the problem begins to converge on a more unsettling possibility. The silence may not be the result of absence, nor solely the result of failure. It may reflect a pattern of behavior shared by those civilizations that do endure. And that possibility raises a different kind of question, one that shifts the paradox from biology and technology into strategy and choice. That shift changes the structure of the problem. Instead of asking how often life appears, or how often intelligence survives, the question becomes how intelligent systems behave when they recognize the presence of others. In a galaxy where resources are finite and distances are vast, any interaction between civilizations carries uncertainty. Information travels at a limited speed. Intentions cannot be verified across light years. A signal received today may have been sent thousands of years ago by a civilization that no longer exists or has already changed in ways that make its original message irrelevant. Under these conditions, even a small probability of hostility becomes difficult to ignore. A civilization does not need to be inherently aggressive to pose a risk. Expansion, resource acquisition, or even defensive measures could create conflicts when multiple actors operate without shared knowledge or coordination. The absence of immediate communication prevents the kind of feedback that stabilizes interactions on smaller scales. There is no rapid negotiation, no real-time correction of misunderstandings. Every decision is made with incomplete information. This leads to a strategic environment where caution dominates. A civilization that reveals its location through detectable signals exposes itself to unknown observers. It cannot predict who or what might receive that information, nor how they might respond. Even if the probability of encountering a hostile entity is low, the potential consequences are difficult to mitigate once contact is established. The cost of being wrong could be irreversible. From this perspective, remaining undetectable becomes a rational strategy. Instead of broadcasting signals outward, a civilization might minimize emissions, reduce its technological footprint, and avoid actions that would create observable anomalies. Energy use could be managed in ways that limit waste heat. Communication could shift to tightly controlled channels that do not leak into space. Exploration might rely on probes designed to remain hidden or indistinguishable from natural objects. This behavior would produce a galaxy that appears empty despite containing multiple advanced societies. Each one, acting independently, arrives at similar conclusions about risk and visibility. The result is not coordinated silence, but a convergence of strategies driven by shared constraints. The absence of signals is not a failure to communicate, but a decision not to. The idea has implications that extend beyond communication. It suggests that the most advanced civilizations may be the least visible, precisely because they have learned to avoid detection. The signals we are capable of observing, broad radio emissions, large-scale energy structures, dramatic alterations to stellar environments, may correspond to early or transitional stages of development. As systems become more efficient and controlled, their external signatures diminish. This interpretation reframes the absence of evidence. Instead of indicating that civilizations are rare or short-lived, it implies that they may be present but deliberately hidden. The silence becomes an active state rather than a passive one. It reflects choices made in response to a perceived environment, not just the outcome of physical processes. However, this raises a further complication. If all civilizations adopt similar strategies, then the first to deviate would be at a disadvantage. Broadcasting signals or constructing visible structures could attract attention without providing immediate benefit. Over time, this dynamic reinforces itself. Each civilization observes the same silence and interprets it as confirmation that caution is justified. The lack of evidence for others becomes evidence that others are also hiding. This creates a stable equilibrium. No participant has an incentive to reveal itself, and no external force disrupts the pattern. The galaxy remains quiet not because it lacks activity, but because activity is conducted in ways that avoid detection. Yet this explanation depends on assumptions about behavior that cannot be directly tested. It requires that independent civilizations, potentially with entirely different origins and evolutionary histories, converge on similar strategic conclusions. It assumes that the risks of exposure outweigh the potential benefits of communication or expansion. It also assumes that these civilizations have the capability to remain hidden effectively over long periods. And there is one more unresolved question. If such a strategy exists, how would we recognize it from within our current observational limits? Because if the silence is not empty, but intentional, then the absence we observe is not a gap in our data. It is a boundary we have not yet learned how to cross. Recognizing such a boundary requires confronting the limits of our own methods. Every search strategy is shaped by assumptions about what should be detectable. Radio surveys, optical scans, infrared measurements, and spectroscopic analysis all rely on the idea that advanced activity produces signatures distinguishable from natural processes. But this assumption may not hold if those activities are deliberately constrained or if they operate using principles we have not yet identified. One of the clearest examples lies in energy usage. Large-scale engineering projects were expected to produce excess heat, radiating in the infrared spectrum as a byproduct of thermodynamic processes. Surveys have searched for anomalies consistent with this expectation, scanning entire regions of the galaxy for stars that appear dimmed or surrounded by unusual emissions. The results have been consistent. No clear evidence of such structures has been found at a scale that would indicate widespread activity. This absence has often been interpreted as a lack of advanced engineering, but it can also be read differently. It may indicate that energy is managed with far greater efficiency than our models assume, or that large-scale projects are designed to avoid external signatures altogether. Communication presents a similar limitation. Early searches focused on narrow-band radio signals, based on the assumption that these would be the most efficient way to transmit information across interstellar distances. While this remains plausible, it is tied to a specific technological pathway. If communication evolves toward methods that minimize leakage or operate through channels we do not monitor, then our instruments would register nothing unusual. Even within our own technological development, communication has shifted toward lower power, more directed systems. Extrapolating this trend suggests that detectability may decrease as capability increases. There is also the question of scale. Human observation is confined to a narrow range of wavelengths and sensitivities. Instruments extend this range, but they are still limited by design choices and physical constraints. Phenomena that fall outside these parameters remain invisible, not because they do not exist, but because they do not interact with our detectors in measurable ways. This introduces the possibility that entire categories of activity could occur without leaving traces we are currently capable of identifying. Attempts to broaden detection methods have led to new approaches, such as searching for atmospheric signatures that might indicate industrial activity. Certain gases, if found in the right combinations, could suggest artificial processes. Yet even here, the interpretation is uncertain. Natural processes can produce similar patterns, and distinguishing between biological, geological, and technological sources requires careful analysis. The absence of clear indicators in these searches does not eliminate the possibility of activity. It highlights the difficulty of interpreting ambiguous data. Another avenue involves looking for transient events, short-lived anomalies that might signal technological processes. However, the universe is filled with transient phenomena, from stellar flares to gravitational interactions. Isolating a signal that can be confidently attributed to intelligence requires repeated observation and consistent patterns. So far, no such pattern has been confirmed. Now, each candidate event either resolves into a natural explanation or remains inconclusive due to insufficient data. This leads to a broader realization. Detection is not simply a matter of looking harder or building larger instruments. It depends on aligning expectations with reality. If the underlying assumptions are incorrect, then increasing sensitivity will not reveal what we are not prepared to recognize. The silence may persist, not because there is nothing to detect, but because we are asking the wrong questions or focusing on the wrong indicators. At the same time, there are hints that challenge straightforward interpretations. Certain anomalies in astrophysical data resist immediate classification. Unusual dimming patterns in stars, unexpected distributions of energy, or signals that do not fit established models occasionally appear in observations. Most are eventually explained through natural mechanisms, but each one demonstrates how easily unfamiliar data can be misinterpreted or overlooked. The process of distinguishing between noise and signal becomes more complex as the search expands. The possibility remains that evidence exists within our data, but has not been recognized as such. Patterns may be too subtle, too rare, or too different from expectations to stand out. This creates a situation where absence of confirmation is not equivalent to confirmation of absence. The boundary between known and unknown is not fixed. It shifts as methods improve and interpretations evolve. But this uncertainty introduces a deeper question. If advanced civilizations can remain hidden within the limits of our detection, then what distinguishes a universe that is empty from one that is full but concealed? Because from our current position, both scenarios produce the same observation, and without a way to differentiate between them, the paradox does not resolve. It transforms into something more difficult to approach, a question not only about what exists, but about what can ever be known. That question forces the analysis into territory where the limits are not only technological, but conceptual. Because even if detection methods improve, even if new instruments expand the observable range, there may still be constraints that cannot be overcome simply by building better tools. Some forms of activity may be fundamentally indistinguishable from natural processes at a distance. Others may operate on scales or in domains that do not produce measurable interactions with our current models of physics. Consider the role of information itself. Every detection method depends on extracting patterns from noise, identifying deviations from expected behavior. But if a system is designed to remain hidden, it would aim to minimize those deviations. Instead of creating signals that stand out, it would blend into the statistical background of natural phenomena. From a distance, it would not appear as an anomaly, but as part of the normal distribution of cosmic events. In that case, increasing observational precision might not reveal it. It would simply refine the background in which it is embedded. There is also the issue of timescale. Human observation spans decades, with some records extending back a few centuries. These astronomical processes, by contrast, operate over millions or billions of years. A signal or structure that appears only briefly in that context could easily be missed. Even if advanced civilizations produce detectable signatures at certain stages, those stages may be short relative to cosmic time. The likelihood of observing them during those windows becomes small, not because they are rare, but because they are transient. This introduces a statistical dimension to the paradox. Detection requires not only the existence of a signal, but the alignment of observation with the period during which that signal is present. If civilizations transition quickly from detectable to non-detectable states, then the observable fraction of their existence becomes minimal. The galaxy could host many such civilizations at different times, but their detectable phases may rarely overlap with our own. Another limitation arises from the assumption that technological development follows a similar trajectory across different environments. Human technology has been shaped by specific conditions: access to certain materials, the presence of an atmosphere, the availability of chemical energy sources, and the constraints of biological evolution. Other civilizations, if they exist, may develop along entirely different pathways. Their technologies might not produce electromagnetic signals in the ranges we monitor. They might rely on mechanisms that do not require large energy outputs or leave minimal external traces. Attempts to generalize detection strategies often rely on identifying universal constraints, such as thermodynamics or the speed of light. So, these constraints do impose limits, but they do not dictate how technology is expressed within those limits. There may be multiple ways to achieve similar outcomes, some of which are more visible than others. Without direct examples, it is difficult to determine which pathways are more likely. There is also the possibility that intelligence itself evolves beyond forms we recognize. Biological organisms may give rise to systems that are no longer tied to planetary surfaces or traditional life processes. Such systems could exist in environments that are currently outside our search parameters. If their activities do not involve large-scale manipulation of matter or energy in observable ways, they would remain undetected. At this stage, the paradox begins to intersect with epistemology, the study of what can be known. The absence of evidence is not merely a gap in data. It reflects the interaction between observer and observed. What we can detect depends on how we look, and how we look depends on assumptions that may be incomplete or incorrect. The silence of the universe may therefore be partly a reflection of our own limitations. However, this line of reasoning cannot be extended indefinitely without losing explanatory power. If every absence can be attributed to undetectable presence, the paradox becomes unfalsifiable. A useful explanation must make testable predictions, or at least constrain the range of possibilities. The challenge is to identify which interpretations of silence can be examined through observation and which remain speculative. Some constraints do emerge from physics. Energy cannot be used without producing some form of waste, even if it is minimized. Information processing requires physical substrates. Movement through space involves interactions with matter and radiation. These principles suggest that complete invisibility may not be achievable. Instead, it may be a matter of reducing signatures below current detection thresholds. As instruments improve, previously hidden phenomena could become observable. This creates a tension between two possibilities. Either advanced civilizations are rare or absent, in which case the silence reflects a true lack of activity, or they are present but operating below our detection limits, in which case the silence reflects a gap between capability and observation. Distinguishing between these scenarios requires identifying signals that cannot be easily suppressed or disguised. And that brings the focus back to the filters. Because if the universe is not empty, and if complete concealment is not absolute, then there must still be stages or processes where detectability increases. The question is whether those stages occur early, late, or not at all. And more importantly, whether we are approaching one of those stages ourselves. If that possibility is taken seriously, the direction of the analysis reverses. Instead of asking why others are not visible, the question becomes what our own trajectory implies about visibility. Human technology has already passed through a phase of high detectability. Early radio transmissions spread outward in all directions, creating a sphere of emissions expanding at the speed of light. For a period, our planet became more visible than at any time before. That phase, however, is already changing. Communication systems are becoming more efficient, more localized, less likely to leak into space. The window during which Earth produces strong, unintentional signals may be brief on a cosmic scale. Energy use follows a similar pattern. As efficiency improves, less energy is wasted as heat or radiation. Large-scale engineering, if it occurs, may prioritize containment and optimization over visibility. The expectation that advanced civilizations would construct enormous, easily detectable structures assumes that scale correlates with progress. But progress may instead favor compactness, precision, and minimal external impact. A system that uses less energy to achieve the same outcome has an advantage, and that advantage reduces its observational footprint. There is also the question of intent. Human decisions about broadcasting signals into space have always involved uncertainty. Some have argued for active transmission, attempting to announce our presence. Others have cautioned against it, noting that the risks cannot be quantified. This debate reflects a broader principle. As a system becomes capable of influencing its environment on larger scales, it must also consider the consequences of being observed. The more advanced the system, the more it has to lose from uncontrolled exposure. If this reasoning extends beyond Earth, then the transition from visible to less visible behavior may be a common stage in technological development. Civilizations might begin in a phase of expansion and experimentation, producing detectable signals as a byproduct of growth. Over time, they refine their systems, reduce inefficiencies, and adopt strategies that limit exposure. The result is a shift from outward expression to inward control. This transition does not require coordination between civilizations. It arises from constraints that apply independently to each one. Energy efficiency, risk management, and long-term stability all favor reduced visibility. The absence of signals, therefore, may not indicate a lack of activity, but the presence of a mature phase in which activity is conducted with minimal external impact. However, this interpretation introduces a critical implication. If visibility decreases as capability increases, then the most detectable civilizations are those in earlier stages of development. Their signals are stronger, less controlled, and more likely to propagate into space. But these stages may be short-lived. A civilization either advances beyond them or fails to sustain itself. In both cases, the period during which it can be easily observed is limited. This creates a narrowing window. Detection depends on observing a civilization during a specific phase of its development. If that phase is brief relative to cosmic timescales, then the probability of overlap between observers and observable targets becomes small. The silence, in this context, is not a permanent state but the result of timing. Yet timing alone may not be sufficient to explain the consistency of the silence across different methods and observations. Even with narrow windows, the scale of the galaxy suggests that some signals should still be detectable. The absence of such signals implies that either the windows are extremely rare, extremely short, or that additional factors further reduce detectability. At this point, the distinction between absence and concealment begins to blur. A civilization that minimizes its visibility may appear indistinguishable from one that does not exist, at least from a distance. The observable universe becomes a surface that reveals only certain types of activity, while others remain hidden beneath detection thresholds. This leads to a more nuanced interpretation of the paradox. The question is not simply where everyone is, but what kinds of presence are compatible with long-term survival. Visibility may be associated with vulnerability, while invisibility may be associated with stability. If that relationship holds, then the silence we observe could be a consequence of selection, favoring those systems that avoid detection. But that interpretation carries a consequence that extends beyond observation. It suggests that the path of development may involve a choice, whether explicit or implicit, between being seen and remaining hidden. And if that choice exists, then it is not only a question about distant civilizations. It is a question about the direction we are moving toward ourselves. That direction is not defined by a single decision, but by a series of incremental choices that accumulate over time. Each improvement in efficiency, each shift toward controlled systems, each reduction in unintended emissions moves a civilization further from detectability. None of these steps are taken with the intention of becoming invisible on a cosmic scale. They are responses to local constraints, energy limits, environmental pressures, security concerns. Yet taken together, they shape the external profile of a technological society in ways that extend far beyond its immediate context. If this pattern is general, then the trajectory toward reduced visibility may not be optional. It may be an inherent outcome of optimization. Systems that waste less energy, that minimize exposure, that operate within tighter margins of control are more stable over long periods. Instability, by contrast, often manifests as excess energy, excess emissions, excess unpredictability. These are precisely the features that make a system easier to detect from a distance. From this perspective, detectability becomes a temporary condition, associated with transitional phases rather than long-term states. A civilization begins with inefficient technologies that produce strong external signals. As it develops, those signals diminish. The period during which it can be easily observed is not representative of its full existence, but of a narrow segment within it. This introduces a selection effect at the level of observation. If most civilizations spend only a small fraction of their lifetimes in detectable phases, then the probability of observing any one of them during that phase becomes low. Even if many civilizations exist, their detectable intervals may rarely overlap with each other or with our own. The silence in this sense is not a reflection of emptiness, but of timing combined with progression. However, there is another layer to consider. Optimization does not only reduce emissions, it also changes the structure of activity. Systems may shift from large-scale, externally visible processes to smaller, internally managed ones. Instead of expanding outward in ways that alter stellar environments, a civilization might focus on maximizing efficiency within existing resources. This could involve dense, localized computation, advanced materials that minimize waste, or forms of energy used that do not produce large, radiative signatures. Such changes would further reduce the likelihood of detection. External observers would see stars and planets behaving according to natural laws, with no obvious signs of intervention. Any artificial activity would be embedded within those systems, indistinguishable from natural variation at the scales we can currently measure. At this point, the paradox takes on a different character. It is no longer solely about missing signals or hidden civilizations. It becomes a question about what kinds of evidence are compatible with long-term survival. If the most stable systems are also the least visible, then the absence of evidence may reflect the presence of stability rather than its absence. This interpretation does not eliminate uncertainty. It relies on assumptions about how different systems respond to similar constraints, and it cannot be confirmed without direct observation. But it aligns with a consistent pattern across multiple domains. Systems that endure tend to minimize unnecessary exposure and optimize resource use. The implications extend beyond astronomy. They touch on how knowledge is interpreted when direct evidence is limited. The absence of observable activity does not necessarily indicate inactivity. It may indicate that activity is occurring within boundaries that prevent it from being easily detected. And that brings the analysis back to the original premise, now viewed through a different lens. The expectation was that the universe should be visibly active if life and intelligence are common. The observation is that it is not. The initial response was to question the assumptions about life and intelligence. But another possibility remains, that the assumptions about visibility are incomplete. If that is the case, then the silence is not a contradiction to be resolved, but a condition to be understood. It reflects the interaction between what exists and what can be observed, between processes that occur and the limits of detection. The universe may still contain what was expected: life, intelligence, activity, but not in forms that produce the signals we anticipated. The absence of those signals does not close the question. It changes it. Because the most difficult possibility is not that we are alone. It is that we are surrounded by systems that have already learned how not to be seen. If that possibility is carried to its conclusion, it does not resolve the paradox so much as invert it. The silence is no longer a gap waiting to be filled. It becomes the expected outcome of a system where visibility carries cost and concealment carries advantage. In that framework, the question shifts from why we do not see others to what conditions would force a civilization to reveal itself despite the risks. One such condition could be limitation. A society constrained by energy, resources, chicha, or stability might be unable to maintain low observability. Inefficiencies would produce detectable signatures as a byproduct of survival rather than choice. In that case, the signals we search for would correspond not to the most advanced systems, but to those that have not yet reached a stable equilibrium. Detection would then be biased toward transitional states, not mature ones. Another possibility involves error. No system is perfectly controlled. Over long timescales, deviations accumulate. A momentary increase in emissions, a structural change, or an unexpected interaction could produce a detectable anomaly. These events might be rare and short-lived, but they would represent points where concealment fails. The challenge lies in distinguishing such anomalies from the vast background of natural phenomena. Without repetition or confirmation, they remain ambiguous. There is also the question of intent beyond caution. A civilization might choose to reveal itself under specific circumstances, if it determines that the benefits outweigh the risks, or if it identifies another system that meets certain criteria. This would require a level of confidence in interpreting distant signals and a framework for decision-making that accounts for unknown variables. The absence of observed contact suggests that either such conditions have not been met, or that the criteria for engagement are more restrictive than we assume. These considerations introduce a dynamic element to the silence. It is not static or uniform, but shaped by thresholds and exceptions. Most of the time, systems remain below detection. Occasionally, conditions may push them above it, briefly and unpredictably. From our perspective, this would appear as a universe that is almost entirely quiet, punctuated by rare, inconclusive events. But even this does not fully escape the constraints imposed by physics. Complete concealment cannot violate fundamental laws. Energy transformations leave traces. Information processing requires physical substrates. Movement through space involves interactions with matter and radiation. These interactions may be minimized, but not eliminated. Over sufficiently large scales or long durations, they should accumulate into observable effects. The absence of such effects at the scales we have surveyed suggests that either the level of activity is lower than expected, or that it is distributed in ways that do not concentrate into detectable patterns. A civilization might spread its processes thinly across large volumes, reducing local intensity. It might operate intermittently, avoiding continuous signatures. It might integrate its activities with natural systems so closely that distinguishing between artificial and natural becomes effectively impossible with current methods. At this point, the paradox reaches a boundary where further speculation yields diminishing returns without new data. The known factors, planet formation, chemical complexity, evolutionary processes, support the possibility of life and intelligence. The observed silence challenges the expectation of visibility. Between these two, multiple explanations exist, each consistent with part of the evidence, but none conclusively supported by all of it. What remains is a narrowing of possibilities rather than a single answer. Early filters may reduce the number of life-bearing worlds. Evolutionary pathways may limit the emergence of intelligence. Technological development may introduce risks that few civilizations survive. Those that do may adopt strategies that reduce their detectability. Each stage contributes to the overall outcome, and the combined effect may be sufficient to produce the silence we observe. Yet the paradox retains its force, because none of these factors can be measured with certainty at the required scale. We do not yet know how common life is beyond Earth. We do not know how often intelligence arises or how long it persists. We do not know how advanced systems behave over millions of years. Each unknown adds uncertainty, and together they prevent a definitive resolution. In the absence of certainty, the silence takes on a different role. It becomes a constraint on our theories, a boundary that any explanation must account for. It forces models to reconcile abundance with absence, potential with observation. It does not tell us which explanation is correct, but it limits which explanations remain plausible. And this is where the reflection begins to carry weight beyond the scientific problem itself. Because the paradox is not only about distant civilizations, it is about how a system interprets its own position when faced with incomplete information. It is about how expectations are adjusted when evidence does not align with prediction. The initial premise assumed that a universe capable of producing intelligence would make that intelligence visible. After examining the constraints, the risks, and the possible strategies, that assumption no longer holds with the same certainty. Visibility is not guaranteed. It may be contingent, temporary, or actively suppressed, which returns the question to its simplest form, now carrying the weight of everything that has been considered. If the conditions for life and intelligence are present, and if the universe has had time for them to develop, then the silence we observe is not accidental. It is either the result of absence or the result of choice. And from where we stand, both possibilities look exactly the same. From that position, the paradox no longer feels like a distant abstraction. It becomes a framework for interpreting our own trajectory. Every new capability we develop, whether in communication, energy use, or exploration, carries implications not only for what we can do, but for how we appear from the outside. The shift from visibility to control is already underway, not as a coordinated effort, but as a consequence of solving immediate problems. Efficiency reduces emissions. Precision reduces noise. Security reduces exposure. Each improvement narrows the window through which we can be observed. If that pattern continues, then the phase we are currently in may be unusual not because of what we have achieved, but because of how observable it still is. A planet broadcasting broadly into space, altering its environment in detectable ways, and experimenting with technologies that produce clear external signatures may represent a brief stage. It is a stage defined by transition between low capability and high capability, found between unintentional exposure and deliberate control. The implications of this are difficult to measure, but they can be framed in terms of probability. If most civilizations pass quickly through this stage, then the likelihood of observing another during the same phase becomes small. The absence of detected signals does not necessarily imply that such stages never occur. It may indicate that they are short-lived relative to the age of the galaxy. Detection, in that case, would require coincidence in both time and method. This interpretation does not provide certainty, but it offers a consistent way to reconcile the available data. It allows for the existence of multiple civilizations while explaining the lack of observable evidence. It does not depend on a single filter or a single failure point. Instead, it combines several factors: rarity of conditions, fragility of development, strategic behavior, and limitations of detection into a cumulative effect. At the same time, it leaves open the possibility that the silence reflects something simpler. It may be that life is rare, or that intelligence is uncommon, or that technological civilizations do not persist long enough to overlap. These explanations remain consistent with current observations. The challenge is that they cannot be distinguished from alternatives without additional evidence. What the paradox ultimately reveals is not just a gap in knowledge, but the structure of that gap. It shows how multiple unknowns interact, how assumptions shape expectations, and how observations constrain interpretation. It demonstrates that absence can carry meaning, but that meaning depends on the context in which it is understood. The opening premise suggested that a universe capable of producing intelligence should make that intelligence visible. After examining the constraints, that premise becomes conditional. Visibility depends on factors that are not guaranteed. It may occur briefly under specific conditions and then disappear as systems evolve. This does not resolve the paradox. It reframes it. The silence is no longer a contradiction that demands a single answer. It is a boundary that defines the limits of current understanding. Beyond that boundary, multiple possibilities remain, each consistent with part of the evidence, none confirmed in full. And so the question returns, not as it began, but with a different weight. If the universe contains other forms of intelligence, then their absence from our observations is not necessarily a failure of detection or a lack of existence. It may reflect processes and decisions that shape how intelligence expresses itself over time. Which leaves one final consideration. The same processes that could explain the silence beyond Earth may already be shaping the future of the only civilization we know exists. If that is the case, then the most revealing answer to the paradox may not come from looking outward. It may come from watching what we become. If that is where the answer lies, then the paradox is no longer something that will be solved at a distance. It becomes something that unfolds over time, within the trajectory of a single civilization, moving through its own stages of development. The silence does not need to be explained all at once. It can be approached as a pattern that becomes clearer as more of those stages are observed directly. At present, the data we have is limited to a single example. One planet, one biosphere, one technological species. From that, models are built, probabilities are assigned, expectations are formed. But a single data point cannot define a distribution. It can only suggest possibilities. The paradox emerges because those possibilities, when extended across the scale of the galaxy, produce predictions that are not matched by observation. Over time, that imbalance may begin to change. Not because new civilizations suddenly become visible, but because our ability to interpret subtle signals improves. Detection does not always require stronger signals. It can also come from better understanding of background processes. Patterns that once appeared random may reveal structure when analyzed with more refined models. Small deviations from expected behavior may accumulate into evidence when viewed across large datasets. At the same time, our own development provides a reference for how detectability evolves. Each technological shift offers insight into how signals are produced, how they propagate, and how they diminish. By observing these changes internally, it becomes possible to model how similar processes might unfold elsewhere. This does not provide direct evidence of other civilizations, but it constrains the range of plausible behaviors. The paradox, then, becomes a comparison between expectation and trajectory. If our own path leads toward reduced visibility, then the absence of detected signals becomes less surprising. If, on the other hand, our development produces new forms of detectable activity, then the silence remains a stronger contradiction. The outcome depends on how these factors balance over time. There is also the possibility that new forms of observation will reveal phenomena that were previously inaccessible. Advances in instrumentation, data analysis, and theoretical modeling may open domains that are currently beyond reach. Signals that are now indistinguishable from noise may become identifiable as patterns once the underlying structure is understood. The boundary between detectable and undetectable is not fixed. It shifts with each improvement in knowledge and capability. However, even with these advances, the paradox may persist in some form, because it is not only a question about detection, but about interpretation. Data does not speak on its own. It must be framed within models that assign meaning to patterns. Different models can produce different conclusions from the same observations. Resolving the paradox requires not only new data, but models that can integrate that data without contradiction. Until that point is reached, the silence remains a constraint rather than a conclusion. It limits what can be claimed, but it does not eliminate possibilities. It forces caution in interpretation, but it does not dictate a single answer. It is a boundary that defines what is currently known and what remains uncertain, and that uncertainty is not empty. It is structured by the interplay of evidence, theory, and assumption. It reflects both the vastness of the system being studied and the limits of the observer within it. The paradox persists because it sits at the intersection of those two scales, where expectation meets observation and neither fully resolves the other. The opening premise suggested a universe that should be active and visible. The observation revealed a universe that appears quiet. After examining the constraints, the risks, the possible strategies, and the limits of detection, that contrast no longer demands a simple resolution. It reveals a range of possibilities, each shaped by factors that are not yet fully understood. Which brings the analysis back to where it began, but with a different perspective. The silence is not just a lack of signal, it is a condition that any explanation must account for. It is a feature of the universe as we observe it, and it carries implications for how intelligence might arise, develop, and persist. If the most advanced systems are also the least visible, then the absence of evidence becomes part of the expected pattern. If intelligence is rare or fragile, then the absence reflects a different kind of limitation. If detection methods are incomplete, then the absence points to gaps in understanding. Each possibility reshapes the question, but none remove it. And so the paradox remains, not as a problem waiting for a single answer, but as a framework that guides inquiry. It defines the boundaries of what is known and highlights the paths that lead beyond those boundaries. If the universe is empty, then the silence is final. If it is not, then the silence is telling us something. And the meaning of that silence is still unfolding. If the meaning is still unfolding, then the paradox is not a closed problem. It is a process that evolves as knowledge expands. Each observation, each refinement of theory, each technological advance adds resolution to the picture without necessarily completing it. The silence remains constant, but the context around it changes. In earlier stages of inquiry, the absence of signals could be attributed to limited data. Instruments were less sensitive, surveys were incomplete, and the number of known planetary systems was small. Over time, those limitations have been reduced. Detection methods have improved, data sets have grown, and the catalog of exoplanets has expanded from speculation to measurement. Yet the silence has persisted through each of these improvements, maintaining its consistency across different approaches. This persistence gives the silence a different kind of weight. It is no longer easily dismissed as a temporary gap in observation. It becomes a feature that must be integrated into any model of life and intelligence on a cosmic scale. Theories that predict widespread, long-lived, and highly visible civilizations must now account for the absence of corresponding evidence. Models that incorporate constraints, filters, or behavioral adaptations align more closely with what is observed, but they remain incomplete without direct confirmation. The paradox also highlights the role of expectation in shaping interpretation. Early estimates were influenced by limited data and optimistic assumptions. As those assumptions are revised, the expected number of detectable civilizations changes. The paradox does not arise solely from the data, it arises from the difference between what was predicted and what is observed. Adjusting the predictions reduces the tension, but it does not eliminate the underlying question. There is a parallel here with other areas of science. When observations do not match predictions, the response is not to discard the observations, but to refine the models. Sometimes this leads to incremental adjustments. Other times it leads to more fundamental changes in understanding. The Fermi Paradox sits at a point where both types of revision are possible. It may be resolved through better estimates of probabilities, or it may require a shift in how intelligence and its consequences are conceptualized. What remains constant is the requirement for consistency. Any explanation must align with both the abundance of planets and the absence of detectable activity. It must account for the processes that lead from chemistry to biology, from biology to intelligence, and from intelligence to technology. It must also consider how those processes interact with environmental constraints, evolutionary pathways, and strategic behavior. Until such an explanation is found, the paradox continues to function as a guide. It identifies where knowledge is incomplete and where assumptions may need to be reconsidered. It encourages the search for new forms of evidence and new ways of interpreting existing data. It does not provide answers, but it sharpens the questions. The initial premise suggested that the universe should be filled with signals. The observation revealed that it is not, and the analysis explored multiple ways to reconcile that difference. Rarity, fragility, concealment, limitation. Each contributes to a broader understanding, but none fully resolves the tension, which leaves the paradox in its current state, not solved, not dismissed, but defined. It marks the boundary between what is known and what remains uncertain. It reflects both the scale of the universe and the limits of observation. It carries implications for how intelligence might arise and how it might persist. And it returns, once more, to the same unresolved point. now informed by everything that has been considered. If intelligence is common, then its absence from our observations requires explanation. If intelligence is rare, then its existence here requires explanation. Either way, the silence is not neutral. It is a condition that shapes the question itself, and whatever answer eventually emerges, it will have to pass through that silence. And that is where the weight of the paradox settles. Not in a single hypothesis, but in the constraint that none of them can avoid. The silence remains, unchanged by interpretation, unaffected by preference. It is the fixed point around which every explanation must turn. There is a tendency to search for a resolution that feels complete, one that closes the gap between expectation and observation. But the structure of the problem resists that kind of closure. Each explanation addresses part of the tension while leaving another part unresolved. Rarity explains the absence of others, but raises the question of why we exist at all. Fragility explains the disappearance of civilizations, but struggles to account for the lack of long-term survivors. Concealment explains the lack of signals, but depends on assumptions about behavior that cannot yet be tested. What emerges instead is a layered understanding. Multiple factors may operate simultaneously, each contributing to the overall outcome. The galaxy may contain fewer habitable worlds than once assumed. Of those, fewer may develop complex life. Of those, fewer still may produce intelligence. And of those, only a fraction may reach a stage of technological capability. Beyond that, additional constraints, instability, risk, strategic choice, may further reduce the number of civilizations that remain both active and detectable. The combined effect of these layers may be sufficient to produce the silence we observe. Not because any single barrier is absolute, but because their cumulative impact narrows the possibilities. The paradox, in this view, is not the result of a single missing piece, but of multiple factors interacting across different stages. Yet even this layered model leaves open the central uncertainty. Without additional data, it cannot be determined which factors dominate, which are secondary, and which may be irrelevant. The balance between them remains unknown. The silence does not reveal the distribution of causes. It only reveals the outcome. This uncertainty is not a weakness of the problem. It is a reflection of its scale. The processes involved span from molecular chemistry to galactic structure, from evolutionary biology to theoretical physics. No single field contains all the necessary information. The paradox exists at the intersection of these domains, requiring connections that are still being developed. At the same time, it imposes a discipline on speculation. Explanations must remain consistent with observed reality. They must account for both the presence of a technological civilization on Earth and the absence of detectable counterparts elsewhere. This dual requirement limits the range of plausible answers and prevents the problem from dissolving into unconstrained possibilities. The opening premise assumed that visibility would follow from existence. The analysis has shown that this is not necessarily the case. Visibility depends on conditions, on timing, on behavior, and on the limits of observation. It may occur briefly under specific circumstances and then disappear. It may never reach levels that are easily detectable across interstellar distances. It may be actively reduced as systems evolve. This shift does not remove the paradox, but it changes its emphasis. The question is no longer simply where others are, but how existence translates into evidence. It is a question about the relationship between what is and what can be known. And within that relationship, the silence remains the central fact. It is the observation that defines the problem and constrains its solutions. It is the constant against which all variables are measured. Which brings the discussion back to its origin, now carrying the full weight of everything that has been considered. A galaxy filled with stars, planets, and chemical potential should, by initial reasoning, produce visible signs of intelligence. It does not. Whether that absence is due to rarity, fragility, concealment, limitation, and or some combination of all of them, it defines the boundary of current understanding. And beyond that boundary, the question persists. Not as a contradiction to be dismissed, but as a condition to be explored. Because the silence is not empty, it is structured. And whatever exists within it, whether nothing or something hidden, remains beyond the reach of what we can currently confirm. Beyond that reach, the paradox does not disappear. It becomes quieter in a different way, less about contradiction and more about perspective. Because once the assumptions about visibility are set aside, what remains is not a failure of the universe to match expectation, but a reminder that expectation itself was built on incomplete information. At the beginning, the reasoning seemed direct. Many stars should mean many planets. Many planets should mean many chances for life. Given enough time, life should develop complexity, and complexity should produce intelligence. Intelligence should leave traces. Those traces should be visible. Each step followed logically from the one before it. The conclusion felt inevitable, but each step also carried uncertainty that was not fully accounted for. The probability of life emerging from chemistry is still unknown. The transition from simple to complex organisms required specific conditions that may not repeat easily. Intelligence, as it exists on Earth, is one outcome among many possible evolutionary paths. Technology introduces both capability and risk. And visibility, which seemed like a natural consequence, may in fact be conditional or temporary. When these uncertainties are considered together, the inevitability dissolves. What appeared to be a straightforward chain becomes a sequence of contingent events, each dependent on factors that may vary widely across different environments. The absence of observable evidence then becomes less surprising, not because it is explained, but because the range of possibilities is broader than initially assumed. Yet the paradox does not lose its significance. It continues to define a boundary between what can be inferred and what cannot. It highlights the difference between potential and realization, between conditions that allow something to occur and the actual occurrence of that event. It also underscores the role of observation in shaping understanding. What is not seen influences interpretation as much as what is. There is also a temporal dimension that cannot be ignored. Human observation represents a brief interval within a much larger timeline. Civilizations, if they exist, may rise and fall over periods that do not overlap with our own. Signals may have been present in the past or may appear in the future. From our current position, we sample only a narrow slice of that timeline. The silence we observe is therefore specific to this moment, not necessarily representative of all moments. This does not weaken the paradox, but it frames it within a broader context. The question is not only where others are, but when they are, and how their timelines intersect with ours. Detection depends on alignment across both space and time, adding another layer of complexity to an already intricate problem. As the analysis extends across these dimensions, the paradox begins to resemble less a single question and more a network of related questions. Each one connects to a different aspect of the problem: formation, evolution, behavior, detection, interpretation. Progress in any one area informs the others, gradually refining the overall picture. But until those connections are fully established, the silence remains the central reference point. It is the observation that anchors the inquiry, the fact that any explanation must accommodate. It does not provide answers, but it defines the limits within which answers must be found. The initial premise asked why a universe capable of producing intelligence does not display it. After examining the constraints and possibilities, that question becomes more precise. Under what conditions would intelligence become visible, and how often are those conditions met? Without a clear answer, the paradox persists. It does not demand resolution on a specific timeline. It continues as a framework for investigation, guiding attention toward the points where knowledge is incomplete. And so the final position is not one of conclusion, but of recognition. The silence is not an anomaly to be dismissed, or a mystery to be solved immediately. It is a feature of the universe as currently observed, carrying implications that extend across multiple fields of study. If the universe is empty, then the silence reflects that emptiness. If it is not, then the silence reflects something about how intelligence exists within it. Either way, the silence is not without meaning. It is the context in which the question continues to be asked. And until that context changes, the paradox remains, unchanged in observation, but evolving in understanding. And that evolution in understanding may be the only form of progress available for now. Not a definitive answer, but a gradual tightening of what remains possible. Each refinement removes certain explanations, strengthens others, and reshapes the landscape of the question without eliminating it. There is a tendency to expect that a problem framed so clearly should yield a clear resolution. The structure of the paradox encourages that expectation. A mismatch between prediction and observation suggests that one of them must be wrong. But the deeper analysis shows that both may be incomplete rather than incorrect. The prediction was built on limited knowledge. The observation is constrained by limited detection. The gap between them is not necessarily an error. It is a space where information has not yet reached sufficient resolution. This perspective changes how the silence is interpreted. It is not simply the absence of signals, but the result of an interaction between processes that generate signals and processes that limit their detection. It reflects both the behavior of potential civilizations and the capabilities of the observer. Neither side can be fully understood in isolation. From within this interaction, the paradox becomes less about a single missing discovery and more about a balance of probabilities. Each factor, formation of life, emergence of intelligence, survival of civilizations, strategies of behavior, limits of detection, contributes to that balance. Adjusting any one of them shifts the expected outcome, but the overall picture depends on how they combine. This is why the paradox remains resistant to simple explanations. It is not governed by a single variable that can be measured directly. It is shaped by a network of variables, many of which are currently beyond precise quantification. The silence constrains this network, but it does not uniquely determine its configuration. At the same time, the paradox has a practical implication. It highlights the importance of expanding both observation and interpretation. New instruments can extend the range of detectable phenomena. New models can reinterpret existing data in ways that reveal previously hidden patterns. Progress may come from either direction or from the interaction between them. There is also a methodological lesson embedded in the paradox. It demonstrates how strongly expectations can influence interpretation and how necessary it is to revise those expectations when they conflict with observation. The initial assumption that intelligence would be visible was reasonable given the information available at the time. The persistence of silence requires that assumption to be reconsidered, not discarded entirely, but adjusted to account for new constraints. In this way, the paradox functions as a corrective. It prevents overconfidence in models that extend beyond the available data. It encourages caution in extrapolation and emphasizes the need for empirical grounding. It does not provide answers, but it shapes the approach to finding them. The opening premise suggested a universe that should be active and observable. The analysis has shown that activity does not necessarily translate into observability. The absence of evidence may reflect processes that limit visibility rather than processes that prevent existence. This distinction is subtle, but it changes the interpretation of the silence. And yet, the silence remains unchanged. It does not reveal which interpretation is correct. It does not distinguish between absence and concealment, between rarity and limitation. It simply persists, consistent across different methods and observations. Which brings the discussion to its final position, not as a conclusion, but as a stable point within the uncertainty. A universe capable of producing intelligence may or may not make that intelligence visible. The absence of visible evidence does not resolve that uncertainty. It defines it. And within that definition, the paradox continues, not as a question that has failed to find an answer, but as one that has not yet reached the conditions required to produce one. Until those conditions change, the silence remains the most reliable fact we have. And whatever the truth may be, it exists on the other side of that silence. And until something crosses that boundary, the paradox remains anchored to a single, persistent observation. It does not fade with time. It does not weaken as theories accumulate. It remains fixed, waiting for evidence that either confirms or reshapes the framework built around it. There is a possibility that such evidence will arrive suddenly. A signal that cannot be explained by natural processes. A pattern that repeats with structure and intent. An observation that stands apart from the background, with enough clarity to resist reinterpretation. If that moment occurs, it will not gradually dissolve the paradox. It will redefine it instantly, shifting the question from absence to interpretation of presence. But there is an equally plausible alternative. No such signal appears. Observations continue to refine the structure of the universe, revealing more planets, more complexity, more detail, but no definitive indication of other technological activity. In that case, the paradox does not disappear. It deepens. Each new discovery strengthens the conditions that should allow for life, while reinforcing the absence of evidence that it has progressed beyond certain stages. Between these two possibilities lies a long interval of uncertainty. During that interval, progress will likely be incremental. Small anomalies will be detected and analyzed. New methods will be developed and tested. Models will be revised, sometimes subtly, sometimes significantly. The paradox will not be solved in a single step, but approached through a sequence of refinements. What makes the problem distinct is that it cannot be isolated from the observer. Our position, our methods, our assumptions, all influence the outcome. The silence is not only a property of the universe, it is also a reflection of how we engage with it. As those methods evolve, the meaning of the silence may change, even if the observation itself does not. This creates a situation where the paradox is both stable and dynamic. Stable in its core observation, dynamic in its interpretation. It remains the same question, but the context in which it is asked continues to shift. The opening premise asked why a universe filled with potential does not display visible intelligence. Do it after following the chain of reasoning through its constraints, uncertainties, and possible explanations. That question no longer points to a single missing answer. It points to a boundary where multiple explanations converge without resolution. And that boundary is defined by what we can observe. If future observations reveal new forms of evidence, the boundary will move. If they do not, it will remain where it is, marking the limit of current understanding. In either case, the paradox continues to serve its role. It does not provide certainty, but it organizes uncertainty. It defines the space within which inquiry operates. It connects disparate fields into a single question that cannot be fully answered by any one of them alone. Which brings everything back to the same central fact, unchanged from the beginning, now carrying the full weight of the analysis. The universe, as far as we can observe, is silent. Whether that silence is the result of absence, limitation, or choice remains unknown. But it is not without consequence. It shapes how we think about life, intelligence, and our place within the larger system. And until something breaks that silence, the paradox remains. Not as a mystery waiting to be solved, but as a condition that defines the limits of what we currently know. And in that condition, the paradox reaches its most complete form, not because it has been answered, but because its structure has been fully revealed. Every path leads back to the same constraint. Every explanation, no matter how refined, must pass through the same narrow point where expectation meets observation and neither fully resolves the other. At the beginning, the question seemed external. It pointed outward, toward distant stars and unseen civilizations. But by the end, it turns inward as well. Not as a replacement, but as an extension. Because the only trajectory we can study directly is our own, and within that trajectory lie patterns that may reflect broader principles. We observe how quickly detectability can change, how a system can move from high emission to controlled output within a short span of time, how technological capability does not necessarily increase visibility, but often reduces it. We observe how uncertainty shapes decisions, how risk influences behavior even when outcomes cannot be predicted with precision. These are not abstract possibilities. They are processes already unfolding. If similar constraints apply elsewhere, then the silence does not require coordination or coincidence. It emerges naturally from the interaction between capability and consequence. Each system, acting independently, follows a path shaped by the same underlying pressures. The result is not a synchronized outcome, but a convergent one. This convergence does not need to be perfect. It does not require every civilization to behave identically. It only requires that enough of them follow similar trajectories to produce a consistent pattern at the scale we can observe. The silence, in that case, is not absolute but dominant. Exceptions may exist, but they are either too rare, too brief, or too subtle to stand out against the background of natural phenomena. That possibility does not close the question. It reframes it into something more precise. Instead of asking where others are, the question becomes what patterns of development lead to detectable outcomes, and how often those patterns occur. It becomes a question about distribution rather than existence, about visibility rather than presence. And within that reframing, the paradox retains its force. Because even if the number of detectable civilizations is small, the scale of the galaxy suggests that it should not be zero. The persistence of silence across multiple methods and observations keeps the tension intact. It prevents any single explanation from fully resolving the problem. What remains then is a boundary that is both stable and provisional. Stable because it is grounded in observation, Provisional because it may shift with new data or new methods. The paradox exists at that boundary, marking the point where knowledge ends and inference begins. The opening premise suggested that intelligence, if it exists, should leave traces. The analysis has shown that this is not guaranteed. Traces may be temporary, minimized, or indistinguishable from natural processes. The absence of clear evidence does not eliminate the possibility of existence, but it constrains how that existence can be expressed. And so the final position is not one of resolution, but of alignment with what is known. A universe filled with potential does not necessarily produce visible outcomes. A lack of visible outcomes does not necessarily imply a lack of existence. Between those two statements lies the paradox, unchanged in its core, but clarified in its structure. It is not a question that has failed to find an answer. It is a question that has revealed the limits of how answers can be found. And until something extends those limits, through new evidence, new methods, or new understanding, the silence remains. Not as an absence to be filled, but as a condition to be understood. Because whatever the truth may be, it is not beyond the universe. It is beyond what we can currently confirm within it. And that is where the paradox reaches a kind of equilibrium, not because it has been resolved, but because every direction of inquiry eventually folds back into the same constraint. The silence does not weaken under analysis. It becomes sharper. It defines the outer edge of what can be inferred, and everything beyond that edge remains speculative, no matter how well constructed the reasoning appears. There is a natural instinct to treat silence as temporary, as something that will eventually be broken by a discovery. That instinct is shaped by experience. In many areas of science, gaps in knowledge have been filled by better instruments, deeper surveys, or new theoretical frameworks. Patterns that once seemed absent were later revealed to be present, but hidden beneath limitations of measurement. It is reasonable to expect that the same process could apply here. But the difference in scale matters. The systems involved are not confined to a laboratory or even a single planet. They extend across a galaxy, operating over timescales that exceed human history by orders of magnitude. The absence of evidence in this context carries more weight, because the opportunity for detection has been vast, even if incomplete. It suggests that whatever processes are responsible for the silence are not localized or accidental. They are consistent enough to persist across different regions, different methods, and different periods of observation. This consistency introduces the possibility that the silence is not merely a consequence of limitations, but a feature that emerges from underlying principles. Not necessarily a single principle, but a combination that produces a stable outcome. Just as physical laws constrain the behavior of matter and energy, there may be constraints, biological, technological, or strategic, that shape how intelligence manifests on a cosmic scale. If such constraints exist, they would not be visible directly. They would be inferred from patterns, from what does not occur as much as from what does. The absence of large-scale engineering signatures, the lack of persistent artificial signals, the uniformity of natural processes across observed systems, these are not proofs of absence, but they are data points that any explanation must accommodate. At the same time, the paradox resists reduction to a purely deterministic model. The variables involved are too numerous, too uncertain, and too interdependent. The emergence of life, the evolution of intelligence, the development of technology, and the behavior of advanced systems each introduce layers of variability. The silence may be consistent, but the pathways that lead to it may differ from one system to another. This suggests that the paradox is not governed by a single cause, but by a convergence of factors. Some may operate early, limiting the number of systems that reach certain stages. Others may operate later, shaping the behavior of those that do. The combined effect may be sufficient to produce the observed outcome without requiring any one factor to be absolute. Yet even this convergence leaves open the question of scale. The galaxy is large enough that even rare events should occur multiple times. If intelligent, technologically capable civilizations exist, even in small numbers, their presence should eventually produce some detectable trace, unless the mechanisms that limit visibility are extremely effective. This is where the idea of equilibrium becomes important. Not a static equilibrium, but a dynamic one. A balance between processes that increase detectability and processes that reduce it. Early stages of development may increase visibility through inefficiency and expansion. Later stages may reduce visibility through optimization and control. The overall pattern depends on how long each stage lasts and how frequently systems transition between them. If the high visibility stages are short and the low visibility stages are long, then the average state of the galaxy would appear quiet. Detection would require observing a system during its brief window of high emission, a window that may not overlap with our own period of observation. The silence in this case is not absolute. It is the result of observing a system at a particular phase. But this interpretation introduces a subtle implication. It suggests that the most advanced systems are not only less visible, but potentially indistinguishable from natural processes at large scales. Their activities may be embedded within the normal behavior of stars, planets, and interstellar matter, leaving no clear boundary between artificial and natural. From our perspective, this creates a fundamental limitation. Detection relies on identifying deviations from expected patterns. If those deviations are minimized or absent, then detection becomes unlikely, regardless of the level of activity present. The universe could contain processes of immense complexity that remain invisible simply because they do not produce the kinds of anomalies we are equipped to recognize. This possibility does not eliminate the paradox, but it reframes its significance. The silence becomes less about absence and more about the relationship between complexity and observability. It suggests that the progression of intelligence may lead away from visibility rather than toward it, a reversal of the assumption that underlies the original expectation. At the same time, there remains a boundary imposed by physical law. Complete concealment is unlikely to be absolute. Energy transformations, information processing, and physical interactions all leave traces, even if minimal. The question is whether those traces accumulate into patterns that can be distinguished from natural processes with current or future methods. If they do, then the silence may eventually be broken, not by a dramatic signal, but by the recognition of subtle patterns that were previously overlooked. If they do not, then the paradox may persist indefinitely, not because it is unsolvable, but because the evidence required to resolve it lies beyond practical reach. This leads to a final layer of reflection, one that connects the paradox to the nature of inquiry itself. Some questions are resolved by acquiring more data. Others are limited by the structure of observation and the scale of the system being studied. The Fermi Paradox may belong to the latter category, at least for the foreseeable future. It does not mean that progress is impossible. It means that progress may take forms that do not produce a definitive answer. It may involve narrowing possibilities, refining models, and improving methods without eliminating uncertainty. The paradox remains as a boundary condition, shaping the direction of research rather than concluding it. And so the silence continues to define the problem. It is not an empty space waiting to be filled, but a structured absence that constrains interpretation. It forces every explanation to account for both what is present and what is not. It connects the existence of a single known civilization with the absence of others, without allowing either fact to dominate the conclusion. Which brings everything back, once again, to the same unresolved point, now expanded across a broader context. A universe capable of producing intelligence does not necessarily make that intelligence visible. A lack of visible intelligence does not necessarily mean it does not exist. Between those two statements lies a space defined by uncertainty, constrained by observation, and shaped by the limits of understanding. The silence is the boundary of that space, and until that boundary is crossed, by evidence, by method, or by a shift in perspective, the paradox remains exactly where it began, unchanged in observation, but deeper in meaning. And as that meaning deepens, the paradox begins to resemble something more than a scientific puzzle. It becomes a lens through which the limits of knowledge itself are exposed. Not in a philosophical sense detached from observation, but in a grounded way, tied directly to how information is gathered, processed, and interpreted across vast scales. Because the central tension has not changed. On one side, there is abundance: stars, planets, chemistry, time. On the other, there is absence: no confirmed signals, no artifacts, no unambiguous evidence of other technological activity. The paradox exists in the space between these two, and every attempt to resolve it must navigate that gap without ignoring either side. What becomes increasingly clear is that the gap is not empty. It is structured by layers of uncertainty that interact with one another. The probability of life emerging is unknown. The probability of intelligence evolving is uncertain. The probability of technological systems persisting over long timescales is unmeasured. And the probability that such systems remain detectable is dependent on factors that are only partially understood. Each layer introduces variability, and together they create a distribution that cannot yet be mapped. This distribution matters because the paradox is not about a single instance. It is about patterns across a population that cannot be directly observed. We are attempting to infer the properties of that population from one example and one persistent observation. That is a narrow foundation, and it limits the conclusions that can be drawn. Yet the paradox does not collapse under that limitation. Instead, it becomes more precise. It defines exactly where the uncertainty lies and what kinds of data would be required to reduce it. It highlights the need for measurements that go beyond detection of planets or basic chemical signatures. It points toward the importance of understanding planetary systems in greater detail, of modeling evolutionary pathways with higher accuracy, of exploring new methods of detecting technological activity that do not rely on assumptions about how such activity should appear. There is also a shift in how absence is treated. In many contexts, absence of evidence is treated as neutral, as something that does not strongly influence conclusions. In this case, the absence is persistent and consistent enough to carry weight. It does not provide a direct answer, but it constrains the range of plausible answers. So it forces models to align with a reality in which detectability, at least as currently defined, is rare or limited. This constraint has implications for how future discoveries will be interpreted. If a signal is detected, it will not simply confirm the existence of another civilization. It will also provide information about how detectability arises, how long it persists, and under what conditions it becomes observable. A single confirmed detection would reshape the entire distribution, providing a second data point that could be compared with our own trajectory. Until that happens, the paradox remains anchored in a single known example. That example carries more weight than it might seem, because it demonstrates that at least one pathway through the filters exists. Life can emerge, intelligence can develop, technology can arise. These are not theoretical possibilities, they are observed facts. The question is how often those facts repeat and how they manifest beyond our own system. The silence suggests that repetition, if it occurs, does not produce widespread, easily detectable outcomes. That conclusion does not require certainty about the underlying causes. It follows directly from observation. The challenge is to determine which combination of factors leads to that outcome and whether those factors are common or rare. As this analysis extends, another dimension becomes more prominent: the role of time not just as duration, but as sequence. The order in which events occur may matter as much as their individual probabilities. A planet may be habitable, but if catastrophic events occur at critical stages, the pathway to complexity may be interrupted. A civilization may develop technology, but if destabilizing factors arise before it reaches a stable phase, its detectable period may be short. Timing interacts with probability in ways that are difficult to model without detailed data. This interaction reinforces the idea that the paradox is not reducible to a single explanation. It is the result of multiple processes unfolding across different scales, each contributing to the overall pattern. The silence is the cumulative effect of those processes, not the signature of any one of them alone. And yet, despite this complexity, the paradox retains a simple core. It is defined by a single observation that has not changed. The universe, as far as we can measure, does not display clear signs of other technological civilizations. Everything else, the models, the hypotheses, the interpretations, exists to explain that fact. Which leads to a final extension of the question, one that moves beyond the immediate problem while remaining grounded in it. If the silence is the result of processes that limit visibility, then those processes may also shape the future of any civilization that continues to develop. They may influence not only how such a civilization appears to others, but how it organizes itself internally, how it manages resources, how it balances expansion with stability. In that sense, the paradox is not only about what exists elsewhere, it is about the constraints that govern existence at a certain level of complexity. It suggests that there may be patterns that apply broadly, even if they cannot yet be confirmed through observation of multiple examples. And the absence of evidence does not reveal those patterns directly, but it points toward their existence. It indicates that the expected outcomes, visible, widespread, long-lived technological activity, are not common, at least within the limits of current detection. That in itself is a form of information, even if it does not provide a complete explanation. And so the paradox remains, not as a contradiction waiting to be resolved, but as a structured problem that continues to guide inquiry. It defines what must be explained, what must be measured, and what must be reconsidered. The opening expectation has been replaced by a more conditional understanding. Intelligence may arise, but its visibility is not guaranteed. Activity may occur, but its signatures may be limited or transient. The universe may contain more than we can see, but what we see is shaped by how that content interacts with our methods of observation. The silence is the interface between those two realities. And until that interface changes, through new evidence, new techniques, or new understanding, the paradox endures. Not as an unanswered question alone, but as a boundary that defines the edge of current knowledge and the direction in which it must expand. And as that boundary continues to hold, it begins to influence not only how the question is approached, but how the entire field around it evolves. The paradox does not sit isolated within astronomy or biology. It extends into every discipline that attempts to understand how complex systems emerge, persist, and interact within constrained environments. It becomes a reference point, a condition that must be acknowledged whether the focus is on planetary science, evolutionary theory, information systems, or even long-term stability of technological societies. Because at its core, the paradox is not just about other civilizations. It is about the relationship between possibility and manifestation. It asks whether the existence of favorable conditions necessarily leads to observable outcomes, or whether those outcomes can remain hidden, suppressed, or transient, despite the presence of those conditions. This question applies far beyond the specific case of extraterrestrial intelligence. It touches on how systems behave under constraints, how they balance efficiency with exposure, and how they evolve over time in response to both internal pressures and external uncertainties. In this sense, the silence becomes a form of data that extends across multiple domains. It suggests that certain expectations about scaling, from simple to complex, from local to global, from emergence to visibility, may not hold in the way they were initially assumed. The transition from existence to detectability is not guaranteed. It may be interrupted, redirected, or minimized by factors that are not immediately obvious when examining individual stages in isolation. This realization has a subtle but important consequence. It shifts the focus from counting potential instances to understanding pathways. Instead of asking how many civilizations might exist based on initial conditions, the question becomes how many pathways lead from those conditions to outcomes that remain visible across interstellar distances. The number of starting points may be large, but the number of pathways that produce detectable results may be small. And this distinction matters because it reframes the paradox in terms of selection. Not selection in the biological sense alone, but selection across multiple layers: physical, environmental, technological, and strategic. Each layer filters outcomes, narrowing the range of possibilities that persist and can be observed. The silence, then, is not simply the absence of activity. It is the absence of outcomes that pass through all these filters and remain detectable at the scale we observe. This layered selection does not need to be extreme at any single stage. Even moderate reductions at each stage can combine to produce a significant overall effect. A slightly lower probability of life emerging, combined with a slightly lower probability of intelligence developing, combined with a slightly shorter duration of detectable technology, can result in a very small number of observable cases. The cumulative effect becomes large even if each individual factor is not. Yet even within this framework, the paradox retains its tension, because the scale of the system remains vast. The galaxy contains enough opportunities that even low-probability pathways might still occur multiple times. The absence of detection suggests that either the combined probabilities are lower than expected, or that additional factors further reduce visibility beyond what is accounted for in simple models. This is where the interplay between theory and observation becomes critical. Theories can be adjusted to match the observed silence, but without independent measurements of the underlying probabilities, then those adjustments remain speculative. Observation, on the other hand, provides constraints, but not explanations. It tells us what is not seen, but not why it is not seen. Bridging this gap requires approaches that can connect these two domains. One direction involves improving the characterization of exoplanets, moving beyond detection to detailed analysis of atmospheres, climates, and potential biosignatures. Another involves refining models of evolutionary processes, using data from Earth's history to estimate how often key transitions occur under different conditions. A third involves expanding the search for technological signatures beyond traditional methods, exploring new ways to identify patterns that could indicate artificial processes. Each of these efforts contributes to reducing uncertainty, but none alone is sufficient. The paradox spans too many scales and variables to be resolved by a single line of inquiry. It requires integration across fields, combining data and models in ways that can capture the complexity of the problem without oversimplifying it. At the same time, there is an inherent limitation that cannot be ignored. Even with improved methods, there may be aspects of the problem that remain beyond reach. The distances involved limit the resolution of observation. The timescales involved limit the ability to observe dynamic processes directly. The uniqueness of our own example limits the ability to generalize with confidence. This does not make the problem unsolvable, but it does suggest that its resolution may not take the form of a single, definitive answer. Instead, it may involve a gradual convergence of evidence, where multiple lines of inquiry point toward a consistent interpretation. The paradox would not disappear in that case, but it would become less ambiguous, its range of plausible explanations narrowed by accumulated data. Until such convergence occurs, the silence remains the central fact. It is the condition that defines the problem and constrains its solutions. It is not an absence that can be ignored or explained away. It is a feature that must be integrated into any understanding of how life and intelligence exist within the universe. And within that integration, the paradox continues to serve its purpose. It highlights the limits of current knowledge. It identifies where assumptions must be tested. It guides the search for new forms of evidence. It connects disparate fields into a single framework that cannot be fully addressed by any one of them alone. Which brings the discussion to its most extended form, where the initial question has expanded into a network of related questions, each connected by the same underlying constraint. A universe capable of producing life does not necessarily produce observable life. A universe capable of producing intelligence does not necessarily produce observable intelligence. A universe capable of producing technology does not necessarily produce observable technology. Between each of these statements lies a layer of uncertainty, shaped by processes that are not yet fully understood. The silence is the sum of those layers, and as long as that silence remains, it will continue to define the boundary between what is possible, what is probable, and what is observable, not as a final answer, but as a condition that every future answer must satisfy.